Alright, so this is a little overview of a project I made that is a smart light bulb that is connected to a command and control server. So here's the basic operation of it. On the left hand side would be the user's network, and on the right hand side would be the internet going out to the C2 server. So how it works is, to the user, the bulb works normally. They can control it from their phone or from their laptop to change the color and everything, and it works normally to them, and there's no indication that it is connected to a C2 server. But then on the C2 server side, the bulb is constantly pinging out to the C2 server to exfiltrate data and to receive new commands. Now this is important that the bulb initiates the connection to the C2 server so that we can get through the firewall. Now, to do this, I had to put custom firmware on it, which involves tearing it down. So on the left hand side, you can see it's just the dome popped off the top of the bulb. The middle image is a photo of the light board, and on the right hand side is a photo of the main board, which for the chip uses a Toya T1 UHL, which uses a Beacon BK7238, which is a newer version of the Beacon BK7231N. If it used the BK7231N, it would be susceptible to a vulnerability called Toya Cloud Cutter, which allows you to install your own custom firmware without getting a UART. But since this uses the new updated chip, we have to get a UART, unfortunately. Speaking of UART, here is how we do that. So on the top left image is where to solder wires and what they do. I did not solder SEN on. That is just to reset the chip without power cycling it. I opted to power cycle it. On the right hand side, you can see the actual solder points that I have. And on the bottom image is the programmer circuit, so that the programmer does not have enough amperage to power the T1 UHL for flash writing. It can dump the contents of the flash without an external power source, however. And the two resistors are important as well. I noticed that when I did not have one, the transmit line was actually backfeeding the T1 UHL, which is causing problems for flashing. And that's the bottom left circuit there with the AMS 1117. That is a 3.3 volt voltage regulator. And then for flashing, I used a chip called LT Chip Tool to flash it. And the firmware I'm using is called Open Beacon. It's an open source firmware for Beacon-based chips. And now time for the demo. Okay, now we're here on my laptop. On the right hand side is the terminal for the server to input commands, and on the left hand side is the output that we will see whenever the light bulbs ping into us. Now they are pinging in every 5 seconds, which in a real world environment you would not have. That'd be too often. You would have it be minutes or hours. Yeah, so if we as you can see, I have the server running on port 443. That is to make all of the traffic look like just normal HTTPS traffic. And I will also add that all of the data being transferred between the bulb and the server is encrypted using 256-bit AES. So if I turn the bulbs on, as soon as they boot up, they should ping in and they should tell me the SSID and the password to the network that they are currently connected to. And if I type in a help in the server, you can see all of the commands that we have. So I'll make bulb 1 do a Wi-Fi scan, and at the same time, bulb 2 can do an IP scan. They can do two completely different things, and these could be on two separate networks. And as you can see on the left hand side, they change from idle to Wi-Fi scan and IP scan, and when it says Wi-Fi scan drip, that means that it is sending me partial results of the Wi-Fi scan because it is not complete yet. And as you can see, I have a lot of access points around me. And once the IP scan completes, there we go, you should see all the IPs that it found on that network. So we got the router, the two bulbs, and my laptop. And now that we have some IPs, let's do a port scan on the router, see what ports it has open. And at the same time, we can have the other bulb do a port scan of my laptop. So as you can see, the router, has the ports open that we would think would have open: SSH, DNS, the web server. And then I have port 443 open. And then as you can see on the right hand side, we can type in view to view data that we have already exfiltrated. And it kind of shows it better than it did on the left hand side. And as you can see, the port scans are different, so they each are saving their own data. Now if I open up Wireshark, I can show you the DOS attack. So my laptop is actually connected with wireless and wired. The wireless is just so that I am a device on the victim network, and the wired is for the C2 connection, which has a public IP address and is plugged into the WAN port of the router. Now if I run the DOS attack on my laptop on port 9000, which I do have open in this case, and we run it for, let's say, a minute. Now if I go to Wireshark, you can see that I am getting flooded with UDP packets. And as you can see, the data just says data exhaustion pulse, but in a real world environment, you can make that whatever you would want it to be. You can make it look like real traffic or anything. So I can have the other bulb do the same DOS attack on me. If I go to Wireshark, you'll see that I'm getting packets from both bulbs now. And then the final command that you would enter is hard kill, which overwrites the first four kilobytes of the app partition, making it so it enters an infinite boot loop. The purpose of this is when in a real world scenario, when you were done exfiltrating data or you're done with whatever mission the bulb was supposed to be doing, you would hard kill it so that it would stop working. The target would think that the bulb just died and they would throw it out. That gets the implant out of the target's building, so that if they ever do try to find anything like that in the future, they won't find it.